We have Yaakov. Yaakov, you're here?
Yeah, I'm here.
Go ahead.
Uri asked me to present Ofra, and I gladly agreed. I'll say what I remember, and Ofra, you'll correct me if I'm wrong on the way. So as I remember, you started, well, I don't remember where you did your first degree, maybe also
100% Huji.
Okay, so first degree at the Hebrew University, then she did a master with Chaim Gewirtzman
And Amitai
Katz on some hydrology process. And after that, she decided to switch to solid rocks and the deep mantle. She did her PhD with Professor Oded Navon and stayed in this area for her PhD, and after that, another 2 postdocs. The first postdoc was with Graham Pearson in Durham University, and I think that there Ofra, something that I really appreciate, paved the way for isotopic analysis of fluid-rich diamonds. And this I really decided to say out loud. Then she came back, she did another postdoc with Ronit Kessel, and after that, she decided to retire and go to work in the laundry in the south, next to Dimona. And she'll tell us today about what she's doing there. So go ahead.
Okay, so I'll compliment a little bit on what Yaakov said. I've been in NRCN for the last 11 years. I'm the head of the Waste R&D unit now, and I also am a senior lecturer adjunct in Ben Gurion, where I teach. So some of my students are in the audience, I could see them. And I'm going to, I wish you to join me for a quest, for a ride on the Israeli way to geological disposal of radioactive waste. And I'll show you some of the work that we have been doing over a little shorter than a decade, and where this way is heading us. And as I said, this is a quest. This is not a work done, and this is not a work beginning. This is a long process that probably going to go on after I'm retired, and I want to share it with you. So the outline of my talk, I'm going to talk a little bit about what is radioactive waste, what are the definitions, and what are the definitions of disposal. We'll talk about the current worldwide picture, a little bit about geological disposal in Israel, what are we thinking about, and we'll take a glimpse on the current research picture. We won't be able to cover all, but I'll show you some of the projects that we are doing. So what is radioactive waste? Radioactive waste is any type of hazardous waste that contain radioactive material. And it has numerous sources: medicine, research, power generation, which is a major source, even mining, rare earth mining, and uranium mining. And of course, we have all the post-Cold War waste in the big countries. What are the concepts we work upon? What are we looking at when we are trying to deal with radioactive waste? First of all, we recognize that this waste is a heritage we leave for future generations. And our work is to protect human health, not only now, but also in the future. The principle that SABA, the IEA, the International Agency for Nuclear Agency, has put is ALARA, as low is reasonably achievable, with an emphasis on reasonably. So the solutions must be aligned with the resources of each country. We cannot expect any other way. The most important thing for me is that Israel strives to follow the guidelines and standards that were formulated by the AAZA and are being applied in the world. So what is the challenge? What is the big challenge we are facing? By the IAEA regulation, the dose rate to the public should not exceed 0.3 millisievert per year in the present and up to 10,000 years in the future. Here we need to make some definitions. First of all, what is a sievert? A sievert is a unit of dose in joule per kilogram, but it's not a physical unit. It's the equivalent biological effect. So it combines the physical unit with a biological prospect. We have no intuition about what this means. This is a lot or a little. So every one of you, just from living in this world, going to the south, taking flights, going to get an X-ray, get every year about 3 millisievert per year. We are talking about 1 order of magnitude lower than what every average person in the world gets from their environment. So virtually no leakage to the environment. The IEA has put a reference system for classifying waste. It depends upon activity in the y-axis and half-life in the x-axis. So if you have waste that is very, very radioactive but decays very fast, this is easy. We can just put it in a shelter and let it decay and no problem for us. If we have waste that may be long-lived but with very low activity, this is also okay. It's exempt waste. Then we go to the central part of this chart where we have low and intermediate level waste that have relatively low activity and relatively low half-lives. And we have the 2 big problems: high-level waste, including spent nuclear fuel, and long-lived intermediate level waste. Those wastes are not are a bigger problem because they have high activity and very high half-life. So we need to take care of them long into the future. So what are the disposal alternatives that the IEA puts through? We have near surface disposal that is adequate for those waste forms that are relatively low in activity, low and intermediate waste form. However, long-lived intermediate waste, spent fuel, and high-level waste are not adequate for near surface disposal and require deep disposal. This is the reason for that is near surface disposal relies mainly on limited time engineered barriers. All engineered barriers that we know, cements, concretes, steels, they are of hundreds to maximum of thousands of years of a barrier. Then they will decay and go away. This is the reason we need something that will last longer for higher level waste. Another important issue is the clearance level at time. The time that the period for institutional control the IEA deploys is 300 years. The reason for this number is the 300 years is 10 half-lives of strontium 90 and 137 cesium, which are 2 of the most important radioactive materials in normal, intermediate, and low-level streams. However, anything that goes beyond 300 years with respect to control, we cannot put within this definition. This is the reason we need a different type of burial system for them. At this point, I like to mention that 300 years ago, we had some Turks here and some camels, no electricity of any kind. And who knows what will be here in 300 years. It's easier to talk about 300 years time spans when you are in France or in Britain, much harder when you're in the Middle East. Okay, how does it look? How does near surface disposal look? So here are a few examples. This is a trench from Australia within a rock, looks like some kind of limestone. You can see a tractor down here like a D9, and you can see that the total for scale, and you can see the total depth of that is probably a few tens of meters. This is how it looks in Israel. This is a trench that was taken, the picture it was taken in the Amine plain in Israel, and you can see it's much closer to the surface. Other solutions are basically building a hill or a mound above the waste form, and you can see the different barriers here, the waste itself within some material, and then different types of engineered barriers sealing the waste from the environment. Okay, I mentioned spent fuel before and said that it was one of the most complicated waste form. So what is spent fuel? And when I said, I talked about this lecture with somebody, said, how does it look? Is it fluid? Is it solid? Nobody can imagine spent fuel. So this is the reason I put this picture here for you. Spent fuel is basically many rods. The rods have small couplets of uranium within them. And this is what goes into a reactor. Okay, a bundle of rods. This is an example I took from the literature on industrial spent fuel, where the original fuel consists of 3% of uranium-235 and 97% of uranium-238. After 3 years within the reactor, this changes. The uranium both fissions and it also provide products that are of higher atomic number due to the addition of neutrons to the system. So what do we get when we look at this waste 3 years after we put it into the reactor, once it's no longer good enough to yield energy, but it's not, it's too radioactive to dispose of in any proper way. So we have uranium-236 that is due to the addition of a neutron to the uranium-235. We have actinides that are the product of neutron addition, mostly neutron addition to the different uranium components. And we have the fission product. So when a neutron impacts uranium, many times it will break it up to two different elements. As we said before, cesium and strontium are common upon these, but there are many others that will be in this group. All these are highly radioactive. So if we look at the original ore radioactivity from which we produced the fuel, and we look at the radioactivity of the fuel the minute it goes out of the reactor and becomes waste, we are talking 4 orders of magnitude more radioactivity. So this is a huge increase. A very important thing to see is we will go back to the ore level only in 10,000 years, and within 300 years, this regulation time of the IAEA will be about 3 orders of magnitude above the ore level. And the ore level is much higher than what the IAEA defines as the allowed dosage to the public, because an ore has more radioactivity than the average environment. So we have to go farther in time, 5, 6, to the 100,000 to 1 million years after the radioactive material comes out of the reactor. It will go back to environmental conditions. This means that shallow disposal is not adequate, and we need to find a different solution, a deeper solution, a geological barrier. So to conclude what I just said, these waste from here, high-level waste, spent fuel, and long-lived intermediate level waste is not adequate for shallow disposal. What are the alternative of deep disposal? What is deep disposal? The emplacement of solid radioactive waste hundreds to thousands of meters below the surface in a stable geological form, where the depths and the characteristics of the host rock provide the isolation rather than the engineered barriers that, as we said, will only last hundreds to thousands of years. So what type of rock are we looking for? What are the characteristics of this rock? It has to have low hydraulic conductivity, so and low water flow within. We want to be in an area where we have very limited groundwater flow or no groundwater flow. A relatively stable geological region with limited fractures and joints that can be conduits for contamination. We will prefer rocks with high partition coefficients towards radionuclides, and we need a unit thick enough to be able to maintain our engineered solution. So whatever solution we choose needs to be put in a specific rock with a specific thickness. In the world, there are 2 main solutions that are being pursued. The first and older one is mine caverns, which we will build a mine at the depth of a few hundred meters, and we will put the waste within it with several engineered barriers, the waste from itself, the canister with around the waste from, the material that will fill the gap between the canister and the wall of the disposal site, and then the host rock itself. The other idea that is younger and came up because of huge financial difficulties for many countries to really build mine caverns is disposal in boreholes. So let's drill a borehole deep enough, hundreds to thousands of meters deep below the surface, and put the waste within it. This is an idea that the Americans have pushed through in the last decade, where they drill extremely deep borehole down to 5,000 meters, and the disposal is taking place in the bottom 2,000 meters. So we're talking something in the range of oil depths borehole. It's very important to note that in Israel, No concept have been selected. Israel has not decided whether they are going to pursue borehole disposal or mine caverns. And we are now conducting research into both solutions. Okay, so let's make a little bit of a comparison between the two solutions. Mine repositories cost a lot of money. We need large upfront costs. It's very complex operation. We need overground and underground operation combined with radioactive operations. We need shafts and ramps. We need mine space. We need ventilation. This is of high hazard and a high cost. Whereas for the borehole, the number of boreholes can be scaled with the inventory. This is very convenient. We can drill a borehole, put all the waste we have to a certain point, wait several years, drill another borehole. So we can really push the money over a lot of time. And we have only surface operations, so we don't have the complexity of underground operation together with radioactive operations. The engineered complexity here that we need a large borehole diameter, and we need to fit only specific waste from in it, because not every geometry of a waste from can go down this borehole. Another important thing is operation time. With a mine repository, most countries talk about 1 century of operation before closure, where with a borehole, it's placed and sealed. We are talking about 1 year of operation for each borehole. And one very important point is the retrievability point, and this is a regulatory point. Many countries demand retrievability of the waste, at least in the operational time. A mine repository enables that to a limit, whereas a borehole makes the waste basically irretrievable. Once it goes down and the borehole is sealed, there's no way to pick it up. So what types of rocks countries select for this for this type of host rock? Salt rock is one of the favorites, because salt rocks, when under a hyperstellar solution, are insoluble and very impermeable. Both the states in Germany have selected this type of rocks for disposal. Clays are also highly thought of, and France is actually building a repository in clay in Bur. Clays have very low hydraulic conductivity, very high KDs to radionuclides, and they heal very effectively from fractures and faults. Another type of rock is granite, where you have unfractured granite. It has relatively low permeability and relatively high KDs, not as good as the clays, but relatively good. The Scandinavian countries, as well as Russia, are looking into these solutions. I'll give you now a short overview of what happens in the world. This is obviously a snapshot of very few cases, just to give you an idea of what's going on. So this is WIP, Waste Isolation Pilot Plant. This is defined as a storage site for post-Cold War transuranic waste only, no spent fuel in here. This is in the States, in New Mexico, and this is the only operational site for waste that is not allowed to dispose of near the surface, that's operating in the world today. It's defined as a storage site and not a disposal site, because regulatory, the Americans could not get the authorization to operate it as a burial site. So everybody operates it as a burial site. The caverns are sealed after they fill up, but it's defined legally as a storage site. It sits within a salt rock at the depth of down to 660 meters. And it's been relatively successful until in 2014, there was an accident. One of those canisters, big barrels you see here, exploded. And the reason for the explosion is that there was radioactive material together with an organic absorbent within the canister. Organic material in the presence of radioactivity hydrolyze and produce hydrogen, and this hydrogen exploded. It closed the operation for 3 years. It cost $500 million to clean the repository, and some of the shafts and tunnels had to be closed. As far as contamination out of the area goes, it was very limited, very trace contamination above the ground, with 17 workers exposed to trace contamination. So this is an operational experience. Accidents can happen even in the most secure places. Next is Finland. Finland is leading the way for the other countries. It's leading in the road for spent fuel disposal in their spent fuel repository named UNCLO. It's designed to be in granite rocks at a depth of 450 meters. And it's supposed to get an operation license at the end of this year and to start operation at 2025. And you can see it's on the beach, very close to the sea. So everything sits basically underneath the sea level with saline water, saline groundwater surrounding it. Germany is our examples for taking one step back. Germany does not have a site for the disposal of high level waste, but it had disposed intermediate and low level waste within mine caverns. They use old mines, old salt mines in the Gulben area, in a mine named Esse2 at a depth of 765 meters. Waste was disposed mainly in the 60s and 70s of the last century. However, the salt appeared to be unstable. The heating of the waste and the water pressures have caused movement and contaminated brine outflow from the area to the environment. Germany is actually collecting the waste and taking it out of this area in order to look for a better solution. And last but not least, and maybe most known by the audience here, is the Yucca Mountain project. Yucca Mountain was a flag project of the US. They have tried on putting a repository at the Yucca Mountain site in Nevada at the depth of 300 meters above water table. All the rest of what I showed you was below water table. This is above water table. It was designed for spent fuel and other high-level waste of civil usage. However, under the Obama administration in 2011, this was terminated, and the US currently has no solution for its spent fuel. All the spent fuel is stored on site near where the power stations are, in canisters above ground. And this is a solution that is not good for a country like Israel, because this is a major danger. Sorry for my son interrupting me here. So let's talk a little bit about reversibility and retrievability. This is a major issue for most European countries. Most European countries have defined retrievability of the waste as a must for the repository, both from security reasons and in the case that we'll find a better solution, or that the waste itself becomes a resource. This puts huge amounts of cost on the design of the repository, because it's one thing to put waste in. It's a completely different thing to take the waste out, especially after closure. So this is one of the regulatory decisions that changes the design of the repository to a very large extent. So this summarizes what we are talking, little story I wanted to tell you about what's going on in the world. And in the next few slides, I'm going to tell you about our attempts to locate a geological disposal site in Israel. So Israel has 2 research reactors operating, no nuclear power generation. So Israel has relatively small amounts of waste. What are our challenges? We have a small country, I'm sure you all know, with a very large population density. And not only the population density is high, the birth rate is high. So we know that areas that are now vacant of people will probably be populated within the next few decades. We have proximity to the Dead Sea Rift and many active faults in Israel. And the common target rocks, those that I showed before, clays, salt rocks, and granite, are not available in Israel in stable areas, in big sections, unfaulted. So we have to look for a different solution. What is a sustainable solution we are looking for? We are looking at the Negev Desert, which is the farthest one in some areas of it from active faults and has the lowest population density in Israel. In the Amine Plain, where NRCN is located, we have the international site for radioactive waste disposal. This site has been operational since the 60s of the last century, and this area is also already licensed for the disposal of waste. So we are conducting a feasibility study for locating a deep waste disposal site within the borders of the Amine Plain. So you all know where the Amine Plain is. The Amine Plain sits between the Hatira and Hatzera anticlines to the south of Road 25. This is basically a very funny definition. South of the road, it's the Amine Plain. North of the road is the Rotem Plain. No geological reason for this separation. This is the area we are looking at. So what are the advantages of the Amine Plain as a waste site? It's very arid, only 70 millimeters per year of rain, average. Potential of evaporation is immense, 2,600 millimeters per year. So we have negligible groundwater recharge. The regional aquifer is approximately 550 meters below surface, and we'll talk a little bit about that in a few slides. We have extensive environmental research in this area for the last 6 years, so we already did a lot of the work needed. It's relatively stable area. When I say relatively, we all know where the Dead Sea Rift is. However, we are 18 kilometers from the nearest active fault, which is within the regulation of the IES for reactors. And this is, of course, a controlled and closed area, so it's easy to protect it for the time. A little bit about the geology, just to remind you, this is a map of the area. This is the Amine Plain, and you can see the Syrian arc structures in the area. You can see the Sinai Negev faults, and you can see the active faults in the area. We have here an active fault in the Sin area, and we have many faults in the Dead Sea Rift area. So we are here. This red line represents a cross-section that I'm showing you here. So how is the cross-section of the area? How does the cross-section of the area looks? We have the Judea and Kornub group in the subsurface. We have the Menucha and Mishash formation. Above it, the Rareb formation. That both both Mount Scopus group units are truncated in the Amine Plain to the east, and everything is covered with the Chatzeva formation. Note that we don't have here any Takia or any Eocene rocks. So Chatzeva sits directly on the Rareb formation. And when we think about a repository, whether it's a borehole or a cavern, we look at the deepest part of this area, which is close to the syncline axis. Okay, I talked about the distance from active fault. So this map shows us the distance from active fault, that's a black line, and the red line is from known epicenters of earthquakes. And you can see we are just off this 10-kilometer buffer. If we look at the western part of the Amine Plain that we will be discussing, it's a little bit more. It's about 18 kilometers from the nearest fault. This is not far, but it's far enough to stand by regulation. Let's dive into the geology of the Amine Plain. This is the geological map of the Amine Plain. We have the Chatzeva formation covering the surface with a Rotem member at the northern part and the Sefa member on the southern part. The conglomerate at the base of Sefa sits directly on the Rareb formation. When we look at the thickness of the Chatzeva formation, here in the slide at the side, you can see it's thickest in the center and western part of the Amine Plain. And it thins to the rims of the Amine Plain, also to the Rotem Plain. It's basically absent in the Rotem Plain. So if we are looking at a relatively thick cover, the areas to look for are the central and western part of the Amine Plain with respect to the Chatzeva formation. We are actually emphasizing and putting our eye on the Mount Scopus group as a possible repository area. Why? Because the Mount Scopus group is relatively deep, 100 to 300 meters below the surface in the western Amine Plain. It has relatively low hydraulic conductivity in most formations, and it's in the Vedu zone. So we have only ephemeral water flow, if at all, and that's a big advantage when we want to dispose of waste. What are the disadvantages? It's fractured, and this is a major disadvantage that we are looking into, a very high kerogen content in these rocks. How does the Mount Scopus group look in the area? We have a big exposure in the Shvela area, and we have exposures in the areas between the monoclines and the synclines of the Syrian arc. And when we do a zoom in on the Yamin plain area, you can see the Yamin, Rotem, Chatrurim basin. At the north of this area, the Rareb formation, so Mount Scopus group and the Rareb formation within them have been metamorphosed and yielded the Chatrurim formation. Southern than that, in the Rotem area, we have exposure of the Mount Scopus group and the Rareb formation. And in the Yamin plain, basically everything is covered with Chatzeva. So we have these relatively unpermeable rocks buried to a relatively large or intermediate depths in the Yamin plain. We are focusing on the Rareb formation. And just to remind you, to those who don't remember, the Rareb formation contains three members. The top one is a chalky member, then a marly member, and the bottom one, and the thickest one, is an oil shale member. The oil shale consists of up to 25% of total organic carbon, and it's composed of type 2S kerogen, where in the marly member we have clays up to 20%, mainly elite, smectite, kaolinite, and polygoskite. And I want to remind you that this formation is truncated in the Yamin basin. So if I go back to this cross-section, you can see that the Rareb formation ends more or less in the middle of the basin. It depends what kind of cross-section you're taking. So the thickest part of it are in the center and western part of the plain. Okay, so these are the structural and Isopark map of the Rareb formation in the Yamin plain. At the left side, you can see the top Judea structural map, and you can see that the Judea rocks are relatively deep at the axis of the syncline, and they are about around sea level, where at the eastern part of the basin, they actually outcrop, and we can see them in the walls of the Chatzera monocline. So this is where we have a very low floor. What about the thickness? So this is the thickness of the Rareb formation, and you can see that the thickest part is in the western part of the basin, near the axis, and it thins out towards the rims. These are data points that came from the work of Minster 1996 on the Rotem plain, and you can see that in the Rotem plain, the thickest part of the oil shale member, together with the relatively large organic material composition, sits right here, right in the continuous area to our polygon here in the western Yamin plain. So we have depth, we have cover, but we also have relatively high amount of organic material that need to be looked at for its applicability for this boson. So this is showing that this is basically continued area, and the thickness shown here in the Rotem plain goes on into the Yamin plain. Little bit about this kerogen. It's a main source of uncertainty about the applicability of this unit. We can see some work down here from Minster 1996 with increasing amount of organic matter in the Rareb formation from top to bottom. This is from a borehole sits within the Yamin plain in the western part of the Yamin plain. And we can see we also have a lot of sulfur, both organic and inorganic. And those two facts have major implications for the disposal of radioactive waste. There are two reasons for it. First of all, radioactive waste releases heat. Heat can pyrolyze kerogen, and we need to estimate whether the heat capacity we will put into the ground will cause any damage, any changes in the kerogen that will yield pyrolysis, which we definitely don't want in this case. The sulfur makes the issue even more complicated because it lowers the activation energy needed for the breakdown, which means that we will need to limit our heat capacity even further. Another complications comes from radiation. Like heat, also radiation can also break down organic bonds and also cause a pyrolysis or breakdown of the material. A little bit about the petrophysics. So this compilation is of formations from the Kunub to the Chatzeva of the permeability and porosity. And you can see that most of the rocks in the area, whether it's the sandstones of the Kunub and Chatzeva, whether it's the limestones of the Judea group, they all have relatively high permeability with a low to intermediate porosity. Whereas the Mishash and Rab formation have relatively high porosity, up to 40–45%, but very low permeability. And this is work that wasn't done in the Amine plain, but from the work of Shitwi 2016 done in the Shfela area, but on the assumption that the rocks are relatively similar. A little bit about the hydrology. So within the Amine plain, we know of a small local perched aquifer, very small, about 1 square kilometers in the northern part of the Amine plain. Whereas we know that we have two regional aquifers, the Judea group aquifer and the Kunub group aquifer. And this is a map we compiled after Gutmann et al. 1998. And you can see that we have separations between the different hydrological basins. And because of the steep slopes here, we have no direct hydrological connection between the different basins, and water flow to the northeast through each basin and drains into the Dead Sea area. You can see it very clearly when we look at the water table in the Kunub aquifer, here in the Sin basin, and here in the Machtesh Katan area, and you can see a dramatic change in elevation, which means there's no hydrological connection between the two. So what do we know about the area of the Yamin plain? Very little. Only one borehole, the FA borehole here to the north of the area, has penetrated both aquifer. You can see that the Judea group aquifer here in green is actually less artesic than the Kunub one. For the Kunub, we have additional points here in the Machtesh Katan area. And from the gradient we calculated for the Kunub, we calculated what will be the depth of water under the Amine plain. I know this is a big assumption, but it's the best we could do with the current data that we have. We came to the understanding that water table in the Safit formation is expected to be at around 565 meters. I would give and take 10% on that and be happy. So, but we are talking hundreds of meters below surface. So this summarizes the short overview of what we know about the Yamin plain. We have a lot of other information that I'm not going to bother you with, but now let's look about what's needed and how do we move to the task of citing a repository. So this is a conceptual repository citing chart from the US, and where in a country a concept is evaluated, whether it's borehole, whether it's a mine repository, the different designs are being evaluated. At the same time, a site is selected, and then the site is characterized and built. In Israel, the site selection was basically done for us, defining the Amine plain as the area we are looking at. We have not started on a concept evaluation yet, and we are now checking both concepts, boreholes and caverns, and we are in the step of site characterization. That's what we've been doing for the almost last decade. It's important to say that all this process, from initiation to the closure and after the closure of the repository, will have to be maintained with research helping it. Just to let you have a glance on what's going on in other countries with respect to development and what kind of timelines we are talking at. So this is an example from Japan. Japan have started the R&D problem in the 70s and is expected to choose a site at 2030. So 50 years from the start of the R&D to the selection of a site. France was slightly faster. They started at the early 90s to define a site, and they are now have already chosen a site, and they are in the process of getting authorization licensing for this site. But in any case, we are talking decades of time from initiation to disposal. Everything we do, all the research we do, and all the information we gain goes into the safety case and performance assessment for the site. We have to show that the site is safe with respect to the definitions of the regulator, time and dosage. We have to run different safety scenarios and show that under different catastrophic scenarios, we are still safe enough. And we have to assess the performance post-closure for many years in the future. We need to model what will happen 10,000 and sometimes even 100,000 years into the future. I don't expect any of you to read through this slide because it's definitely too small even for my eyes. But this is a concept of how to design a safety case and performance assessment done by the Americans. And we are very happy to have the help of the Sandia National Lab people helping us to design this safety case for us. So now in the last chapter of my lecture, I will take you through a little bit of the research done by us in the last few years to give a good safety case and performance assessment on this site. We are looking at the waste, we are evaluating waste form, looking at the waste from rock interactions, looking at the rock sorption properties, how radionuclides migrate in those carbonate rocks, fractured carbonate rocks. What are the rock mechanical properties? What kinds of engineered assistance we will need? Hydrological modeling is done. And as I said, we are looking on the impact of organic matter. I have much more than I can show, so we'll start. And when you think I should stop, just raise your hand, Uri, and tell me. So waste form evaluation, what is a waste form? When we have radioactive waste, we want to stabilize it within a matrix that won't let it migrate. And we have several matrices that are acceptable in the world, where cementitious material are the most common one for low and intermediate level waste. However, cementitious material have very high pH, and high pH perturbates the rock, the surrounding rock area. The rocks are normally, when we are talking about carbonates, about 8, the pH of 8, and the cement can be 13, 12. So we need to decrease the pH of the cement in order to make it more adequate for the carbonate area. So this is a work done by my student, Martin Scheiner, who's here in the audience, I think, together with BGU University and the IRSN in France, where we dope cements with strontium, as I said, a very common radioactive material. We are working, of course, with a simulant, and we look at the leaching ability, at the retention ability of these matrices. And although the materials that have low pH have significantly higher porosity, both in the macro and the micro scale, they are much less leachable, and the waste is retained to a much better level than in the normal cementitious materials. Another work that we are conducting is work on a different type of retention material that is called geopolymers. And geopolymers are basically silica aluminate matrices that are designed they are similar to zeolites, and we make them from the mixture of amorphous silica alumina source, such as metakaolin, such as fly ash, with a base. And they form an amorphous material, amorphous polymer-like material, inorganic polymer, that has a good retention ability and has a longevity, a longer time span than cements. And I just wanted to show you some of the tools that we use to estimate the compliance of this material. We basically use geochemical modeling on specific framework designed for cements and geopolymers, and specific databasing like SEMdata with a software called GEMS, also with Frixie, to simulate how contaminants will be released for the matrix and what are the best conditions for the matrix to be stored at. And this example shows the retention of cesium, as I said, another important contaminant. And you can see that when we have high nitrite content in the geopolymer, which happens because of the radioactive streams, we have less retention than when we have no nitrite, and we could very nicely simulate the results. Okay, so now we have a waste form. How will it relate to our rock? This is the work we are conducting together with the Vanderbilt University and the Sandia National Lab, when we took rocks from the Mount Scopus group, 5 different types of rock, and casted cement upon them, and let them age for about 18 months in a controlled environment, and then put them in the microcity to see what happened in the interface. And we got a lot of interesting results. We have precipitation in some of the area. However, in other areas, and it's hard to see, but we have here black lines, we have decoupling, and basically we have cracking. So this interface between the cement and the rock might actually become a conduit because we have some decoupling in this area. All this data is being modeled for deposition and of the material. This is the simulation done, shows how much volume is added on the cement side after a certain amount of time. This work, I know that many of you knows Chen Gruver, that graduated in BGU. He is a postdoc in this project, working now in Vanderbilt University. Okay, so we have a waste form. We see how the waste form or the cement interacts with the rock. Now we have to look at the rock itself, right? So we did several projects on the rock sorption properties. This is a work by a student of ours, Emily Tren. She did the work in Sde Boker with Noam Weisbrod, me and with Nadia from the Geological Institute. And she looked at the sorption of uranium and cesium to bentonite colloids, because bentonite is many times the sealing material within a repository or within a borehole. And what she showed, that under the conditions that are common for the repository, the uranium and cesium make very different ions. The uranium couples with the carbonate and calcium and make a large three-component ion, while the cesium is basically cesium plus, as it should be. However, at some point, they sorb to the same site, and we saw computational sorption to the bentonite colloids between the cesium and the uranium. This is one part of Emily's work. Oops. And the other part of Emily's work have looked at the migration of radionuclides in carbonate rocks. This work was done both in a lab scale in a fractured chalk column, where we've flown different solution with contaminants and with colloids through and looked at the breakthrough curve and understood the chemistry and the hydrology of them. And after this work was done and the concepts were understood, we have gone upscale and did work in the field, where we injected solutions with colloids and simulate contaminants in the Ramat Chovav area, Neot Chovav it's called now, and pumped them downstream in another borehole, and saw the response. Emily have very successfully graduated her PhD a couple of months ago, and now is in Colorado, published many articles on this subject to whoever is interested. It's important to say that in her work, she worked in collaboration also with the Lawrence Livermore National Lab, and went there for about 3 months to do work on hot materials, so on real live isotopes rather than simulants. Uri, when I'm over time, let me know, because I can go on. Now I'm going to touch on, Ma?
Go ahead, you're good.
Okay, so I'll give you a glimpse on 2 other subjects that I'm not personally studying, but our group is working on, and we have, of course, people doing the work. A little bit about the rock mechanical properties. So in a collaboration between the Geological Institute, the Eyal Shalev, and the Sandia National Lab, we are testing the thermal behavior of the rocks, especially the organic rich rocks, and we looking about the thermal diffusivity and different thermal parameters to put into modeling for these rocks for the long term. Moreover, they have been doing 3D experiments to check the strain stress behavior, and have shown that basically these rocks go to about 0 porosity and actually lose kerogen when they are compacted. So we have a problem or a notion that if those rocks are compacted at some point, kerogen can actually migrate out of the rocks. All this work in the rock mechanical perspective, we are also doing modeling work. This work is being done in BGU by Shmulik Pinkhart and Yossi Chatzor, where they do simulations for us of different types of concepts for disposal, whether it's a tunnel, as in here, whether it's a borehole, what will the stresses around the borehole will it be stable or not stable? And actually the results show that within the Garb formation, we will need a lot of engineered barriers, and we are very close to failure. So these rocks are not very good in holding large vacancies within them. These rocks are relatively weak. Okay, one last thing I wanted to show you is the work done on the hydrological model for the Vedu zone in the Amine plain. This work is done or is headed by Ravid Rosenzweig from the Geological Institute, Noah Balaban from NRCN, and people from the Los Alamos National Lab. And they have been able to build a model, a 3D model for the Amine plain based on all the information we have, do some just statistical analysis, and even run simulations for infiltration, different infiltration scenarios within the area with different amounts of rain and different time spans. And the most important thing for me to take home, and this is initial results. This is not published data yet, and we are working on that we don't have to go far from the current climate conditions to be in a condition that we have flow into the aquifer. Right now, we have very little water coming in and very high evaporation. We probably have very close to 0 recharge. However, if we go to about 200 millimeters per year, so 3 times the amount of rain we have now, so basically Kiryat Gat, Beersheba area, not too far away, this will already cause infiltration, which will makes us look about the migration of radionuclides under these conditions. So, to summarize, the IEC is studying the Vedu zone in the Amine plain as a host rock for deep radioactive waste disposal. And the Rav formation is being considered as a possible host rock, where we know we still have a lot of unknowns and a lot of big questions. No decision concerning the disposal code concept has been taken, and in-depth scientific understanding is needed to develop the safety case and performance assessments for the disposal. I tried to show you that we have recruited a lot of forces for this task. People within Israel, especially from BGU and the Geological Institute, and people out of Israel, people from the French authorities, the CEA, IRSN, from the American NSA labs like Los Alamos, Lawrence Livermore, and Sandia, and we need all the data we can gather. Multidisciplinary effort of the professional community is needed, and really I'm here to ask you guys, if you have good questions, if you have good ideas, if you have good proposals, come talk to us. This is going to be around for many years to come, and I think this, if I can say one personal word, for me, this is the biggest thing I will live as a scientist if I make Israel make a big step forward towards geological disposal. Thank you.
All right, thank you so much, Ofra. It was great. And questions. I know I have some, but if you have a question, you just unmute yourself.
I want to say one more remark. I haven't mentioned all of my co-workers In name, there are many, and I don't want to insult anybody. One person I do want to say his name, I think he's here in the audience, is Rani Calvo. He's been with us from the start and has done much of the work and the maps you've seen. I need to acknowledge him.
I have a question.
Yeah.
Go ahead.
עופרה,
כן, כן.
מה שלומך?
ברוך.
Okay, I will ask in Hebrew. So, הרי לפני הרבה שנים, כשאני עוד הייתי תלמיד, אז היה טד רינגווד, ואני מניח שאת בוודאי עוד איכשהו זוכר את השם שלו, ויאקי בטח חייב לדעת את זה. טד רינגווד, מי שלא יודע, הוא באמת אחד מהאנשים החשובים ביותר בתולדות מדעי כדור הארץ, ואבי הפטרולוגיה האקספרימנטלית. והוא, אחרי שהוא יצא לפנסיה באחרית ימיו, הוא עבר לתחום הזה שאת מתעסקת איתו עכשיו, והעניין שלו היה, מכיוון שהוא עבד על מינרלים שהתגבשו בלחצים וטמפרטורות מאוד גבוהות בתוך המעטפת, אז העניין שלו היה לקחת את המינרלים האלה ולראות האם להשתמש בהם להטמנה של פסולת גרעינית. יש לך מושג לאן זה יתקדם?
Yeah. So, English or Hebrew? I can do it in English. So, those minerals have been researched. So, when we look about retention matrices for radioactive waste, we are talking about three types of materials: cementitious material, glasses, and specific minerals. The big problem with specific minerals that they have amazing retention capacity. But when you want to make a huge amount of perfect minerals on or crystals on an industrial scale in a radioactive environment, that becomes a task that is very hard to make. And it's very hard to assess the safety of it, because it's enough that some of the crystals are not perfect and you'll get significant leaching. What happens that most countries have, so work on that has been through the last 50 years and it's still on, but it's never gone to an industrial scale. It's always on the lab scale. People in the world for low level waste, Moti, לא שמעתי.
You are giving a general answer. You are giving me a general answer. I'm asking specifically about Ted Ringwood. What happened with Ted Ringwood's experiment?
So a lot of work was done on perovskites. That it was, if I remember rightly, recall he worked on perovskites as retention matrices. It works. What? It's not possible to do it industrially.
Okay.
Okay.
אורי, יש לי שאלה אם אפשר לשאול?
Go ahead.
שלום עופרה, תודה רבה על ההרצאה. השאלה שלי זה, את מניחה שבמישור ימין יש לך אזור בלתי רווי בשכבות שאת מדברת עליהן. השאלה שלי זה מה הבסיס של זה, ואני אסביר. מישור רותם הרי צמוד למישור ימין, ובמישור רותם אנחנו יודעים שיש לנו את אקוויפר המשש. אקוויפר המשש שם מזוהה מאוד מהתעשייה של מישור רותם. גם בסינקלינה שמדרום, בתוך נחל צין, בין רכס חצרה לרכס מחמל, בסינקלינה שם גם כן אקוויפר המשש הוא רווי במים, והם הזדהמו שם, אנחנו יודעים מה קורה בין צין ובין עקרבים. לכן אני שואל, מניין לנו שהאזור הבלתי רווי, שאת מדברת עליו הוא בלתי רווי, זאת אומרת, האם אין אקוויפר שעון במשש, בסינקלינה של אורון אפעה, ימין ורותם, זה סינקלינה אחת. רגע, עוד דבר אחד, אנחנו יודעים גם שהאקוויפר המשש הזה, הוא דולף לתוך אקוויפר יהודה, מכיוון שהמנוחה, יש בה הרבה מאוד מערכות צנרת, קרסטית עתיקה, ואנחנו יודעים שיש את הזיהום של קידוחי אפעה, שירדו לאקוויפר צפית ולאקוויפר חביון, וזה הגיע עד ים המלח. זאת אומרת שיש שם זיהום גדול מאוד של אזור התעשייה רותם. עכשיו, אני לא יודע אם יש הבדל גדול בין אזור התעשייה רותם למישור ימין, הם מחוברים, הרי סך הכל זו אותה סינקלינה, אותה מערכת בדיוק. בקיצור, מה הבסיס להנחה שלך שזה אזור בלתי רווי ללא אקוויפרים שעונים במשש, ואולי גם במקומות אחרים? אז
קודם כל תודה על השאלה, כי זה נושא שלא הכנסתי אותו, אבל אנחנו כרגע מתכוננים לקראת קידוח אפיון באגן, בדיוק באזור שאנחנו מדברים עליו, כאשר יש לנו בדיזיין של הקידוח שני סנריואים, סנריו שבו מוצאים מים במשש, בדיוק כפי שהזכרת, וסנריו שבו לא מוצאים מים במשש. עכשיו, ממה שאני קראתי, מים במשש נמצאו בעיקר באמת באזור של אגן סין ודרומה, ופחות ב-FA. ב-FA לא ראינו מידע, אני לא ראיתי, אבל אם אתה יודע שונה ממני, אני אשמח. ב-FA לא ראיתי מידע על מים במשש, אבל עוד פעם, זה בדיוק הסיבה שהעליתי את הדברים. אם יש מידע כזה ואני לא מכירה אותו, אני מאוד אשמח לראות אותו, אבל אנחנו לגמרי מתייחסים לזה. זה מבחינתי, דרך אגב, מבחינתי, זה כמעט no go. אם יש לנו אקוויפר פעיל של מים שהם עלולים להיות ישימים שם, זה מאוד מאוד בעייתי מבחינת היחידה. חשוב לי להזכיר פה נקודה אחת. כל העולם לבד מהתוכניות של ארצות הברית, טומנים מתחת למפלס מי התהום. מהסיבה הפרוזאית שאין להם אזור בלתי רווי, אוקיי? או האזור הבלתי רווי שלהם מאוד מאוד דק. כלומר, יש פתרונות טובים להטמנה באזור רווי. באזור שלנו, שיש לנו כל כך הרבה אזור בלתי רווי, שנותן לנו סוג של בופר מאוד משמעותי, עדיף לנו ללכת על אזור בלתי רווי.
תודה.
Okay, more questions. I have a question. So what about recycling? I mean, in the waste, there's still quite a lot of uranium that can be useful, probably more than ores. Why not recycle it?
Okay, so this is a big question, not really related to Israel, but related to the world. The term you are looking for is reprocessing of spent nuclear fuel. Reprocessing have been done and is being done in France for many years. France is taking all of their spent fuel, melting it again, and making new fuel out of it. It's called MOX. It reduces the amount of spent fuel at about 10 times. So it's a very effective process. However, this is one of the most hazardous toxic processes that you can imagine. And moreover, this is the process that yields nuclear weapons. So most countries in the world does not want to go and deal with that. In America, it was done in the 70s and then was outlawed. And in Germany, it's outlawed. And it's outlawed not from engineering perspective, but from political and safety perspectives.
Okay, thank you. We have time for one more question.
Can I say something?
Go ahead.
Okay. Can you hear? Yeah. Okay. In the Shfela, about maybe 10 years ago, there was this major project of producing hydrocarbons from oil shale. And these high-grade oil, and I understand that this project did it with using a unique technology which was far away from fracking. It was essentially heating it, preheating, in order to produce all the oil shales. And a lot of study was done on the stability of the remaining less hydrocarbon containing chalk, basically raw chalk. Are you considering the possibility that if you're going to use this oil shale, basically, for this purpose, preparing the oil shale by removing, either using or whatever, burning off the hydrocarbons, and thereby creating a much more stable environment in which you could perhaps store this horrible stuff without worrying so much about the volatilization of the host rock. This is not so much a question, but just a suggestion.
Okay, so first of all, we are very aware of the work done, and some of the people that were employed in this project are actually working for us, people in the Geological, working with us, people from the Geological Institute, like Yoav Rosenberg and Itai Reznik, and we are using their data and knowledge to a large scale. Second of all, if I had to choose a process, what you suggest is basically decreasing the volume of the unit significantly, causing a lot of changes in the unit, causing fracturing. and changing all of its conditions and then putting waste in it. I wouldn't do that. I would choose a different unit that doesn't need to go through all this very complicated and dangerous process. If you rightly recall, the process in the Shfela fell off because there was no public acceptance for it, and the public basically killed it. I see it's very unlikely that such a process could be a lead for geological disposal. If this unit proves not right or inadequate, we will have to go and look for other units or other locations. This is my main message. We want to make safe solutions.
Thank you.
Thank you. Okay, I'd like to thank you once again and thank everybody for joining us. And we're going to meet again after Passover. Okay, תודה עופרה.
Bye. Bye.
ביי, להתראות.
תודה רבה.